Welcome back to another episode of text processing and analysis. In this video, we will look at lesson 12.2 on fuzzy string matching. So let's get rolling. The objective is that students will use fuzzy string matching, to determine the similarity of strings based on edit distance. Okay, and I'm zoomed in a tad bit too much. Okay, so this question right here, what question does string one double equal sign string two answer? What is the question that expression in Python answers? What do you think? One variable that's holding one string, double equal sign, another variable holding another string. That answers the question of whether string one is identical to string two. Every last bit of it is identical to the other string. And it returns a Boolean value of true or false, right? Okay. Well, fuzzy matching answers the question, how similar is string one to string two? And it gives you, the package I'll show you, the module I'll show you, gives you a score between 0 and 100. The closer to 100, the more similar they are. 100 would be they're identical, according to the certain algorithm used, and 0 or closer to 0 would be they're very different. And so the package or the module that we'll use uses the Levenstein distance, edit score distance. And it is a way, it's the distance between two words. The Levenstein distance between two words is the minimum number of single character edits, whether insertions, deletions, or substitutions, required to change one word into the other. It's named after this Soviet mathematician, Vladimir Levenstein, in 1965. Okay, and so here's some details about it. So for example, here from kitten to sitten has an edit score distance of 1 because there's one substitution. Or sitten to sitten, there's a 1 character substitution there. Or here, sitten to sitting with a G at the end, there is a 1 character insertion. So anyway, these, it's based on this idea of how many character either insertions, deletions, or substitutions do you need to change one string into another? That's called the Levenstein edit distance. And the Python module called the fuzz implements the Levenstein distance algorithm, and it provides 6 useful functions. So here it is, the fuzz. By the way, it was formerly called fuzzy wuzzy. So you'll see many references to fuzzy wuzzy. Okay. It uses the Levenstein distance, like I mentioned, and it provides 6 very useful functions that under the hood implement the Levenstein distance score, but in the end give you a score between 0 and 100. Okay. So here are those 4 functions, well, the 4 of the 6 here: simple ratio, partial ratio, token sort ratio, and token set ratio. And then 2 more down here, the extract and the extract one are very similar. Okay, so those are those 6 functions. And here's a good blog post. This blog post is somewhat dated, but the information is still very, very useful and very accurate. So they give the example here of trying to find tickets for a Cirque du Soleil event or performance. And if you find this string here, Cirque du Soleil, Sarcana, New York, that first string is different from the second string, right? And so if you use the double equal sign, it would say false. This string is not like the other, not identical to the other. But with the fuzzy string matching, we could say, you know, if we're getting a high score because Cirque du Soleil, Sarcana, those characters are in here as well. They're in the first one as well as the second one. And so this is where fuzzy string matching could be useful, is to find strings that are similar, but not identical. And, you know, looking at these different strings, we'd say, oh yeah, these are referring to the same concert. Great. So they talk about this in this blog post. Okay. So if you like to read through that, feel free. And other programming languages also have fuzzy matching ability. In R has a fuzzy string matching module called, I think it's string dist for distance, string dist. Yeah, string dist. Julia has one as well. Other programming languages have them. Okay, so let's jump into an activity here. It says, I say, take a few minutes to run the example code for each of the following 4 functions. And importantly, understand and explain to a neighbor or to yourself, whatever, what each function does. So I have a link here to the first function, which is ratio. And you can see that you can just kind of see the output itself. If you want to run it, you sure can. In Python, you would need to, let me scroll down here. You need to pull these things in first, these import statements there. But if you can just look here, okay, what is simple ratio doing? What is 97 about this string and that string? You can see that they're identical except for the exclamation point on the second one. And then what is partial ratio doing here? It's the same 2 strings, but now we get 100. What's going on there? And then, so just go through and look at these and try and just hypothesize, like, okay, what's happening here? Well, I think this is what it's doing. That's why I'm getting 100, which is a perfect match. Not a perfect match, but a perfect, the highest score they can give. Right? The scores go from 0 to 100. And then try it with the token sort ratio and the token set ratio. Okay. So give that a try for a few minutes here on this activity. Ready, set, pause the video. Okay, welcome back. So if we look at those, let's look at the ratio, the simple ratio. It gives it a score of 97 because they're very close to each other, right? The only difference is that one exclamation point. So there are 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If I did that counting correctly, there are 14 characters that are identical, and the 15th character on the second string is the only difference. So there's a really high score. It gets a really high score of 97. Okay, so what is partial ratio doing? We got 100 here. Well, what this means is that it looks at the shorter token or the shorter string and says, is this shorter string within the other string? And it found the shorter string, which is, this is a test. It found that exact sequence of characters, including the spaces, within the larger string here, right? And so that's why I returned 100. Like, that's the highest score it can give. If it found the entirety of the shorter string within the longer string. That's why I gave 100 there. And then the token sort ratio is the second one listed here. They have the simple ratio as a comparison here. So what is this doing? Well, what it's doing is, it is, first of all, tokenizing. It says token here because it tokenizes, which means it breaks up the string into words. And it also gets rid of punctuation. It keeps numbers, Arabic numerals, and characters, alpha characters, but it gets rid of punctuation. They don't have any punctuation here, but I'll show you in a second that it does get rid of those. So it first tokenizes them and then sorts them and then finally compares them. So the fact that we got fuzzy, wuzzy, was a bear, but over here in the second string, we have wuzzy first and then fuzzy, which is different from the first string, right? But it doesn't matter because it's going to tokenize these strings into words and then sort them in alphabetical order. So it's going to have a, bear, fuzzy, was, wuzzy, right? It's going to tokenize and then sort. So it doesn't matter that they're out of order because it'll sort them. That's why we get 100 here. The highest score is 100. Okay. And then the last one here, token set ratio. Again, it tokenizes. That's what that means. So it breaks it up into alpha numeric strings on spaces, but it also gets rid of punctuation. And then the set, I don't know if you remember, the set data structure in Python is a data structure that gets rid of duplicate elements. And so the fact that we have 2 fuzzies on the second string means that once we take the set, that is, we get rid of duplicates, it's going to erase one of those. It's just going to keep one of those two fuzzies, and so it will be identical to this one. And so it's very much like the token sort in that it tokenizes and it sorts, but then it also gets rid of duplicates. And so it's going to get rid of the second fuzzy here, and then alphabetize the words first, bear second, the one fuzzy that's left third, and then was, and do the same thing over here. And so that's why we get 100, the highest score over here with that one. Okay, I think I have that coded up in my solution file, pretty sure. Yeah, I mean, basically I just simply put in what they have on that web page there. But here I have it in code. Let's just run it for fun. And yeah, we get the numbers that they report over there, if I'm not mistaken. Yeah. Okay. So that is how those work. Again, like I mentioned, it's using Levenstein distance under the hood, but it doesn't report the actual number of character insertions or deletions or substitutions. It puts it onto a scale between 0 and 100. All right, now take a few minutes here to understand what extract and extract1 are doing. If you look back on the web page, I have a link on these exact function names. Just take a minute to understand what's happening here. What are they trying to do with these extract and extract1 functions? Okay. So take a few minutes here on this little assignment or little activity there. Ready, set, pause. All right, welcome back. Let's take a look at their extract here. So what this is showing is that, by the way, this process, let me just scroll back up. You need to import this one here from the fuzz import process, which is an object that has this method of extract here. It says, hey, take this string, look in this list of other strings and limit it to 2 and give me the top 2, the 2 that are most similar to this string I gave you. And so the choices here are 4 NFL teams. Let me just go over to my solution file so that we can look at it once without me having to scroll to the right there. Let me just come down here and I'll just grab this one for now. Put it in here. Nope, that didn't work. Let's grab that. Come in here, do all. Okay. So on line 3, I have choices. I have 4 NFL teams: Atlanta Falcons, New York Jets, New York Giants, and Dallas Cowboys. And then here on 4, I say, okay, process, which I import above, extract from the choices, the one choice among those 4 that looks most like, or the two that look most like New York Jets. And when I run it, I get a score of 100 here for New York Jets. See that right there? Because after dealing with capitalization, it finds a perfect match. This right here, New York Jets uppercase, capitalized, that is, it's identical to the lowercase version of it after it deals with capitalization, right? So we get 100, a score of 100, which is the highest score. Then also it found New York Giants here and it gave it a score of 79, which is high. And this, you can change this limit. I'm going to change it from 2 to 3 and then rerun the script. And I get one more back, and it thought Atlanta Falcons had a score of 29, not very much like New York Jets. Once again, the range is from 0 to 100, 100 meaning like a perfect match. Okay. And then the extract1 is basically the extract with a limit of 1. Let me just grab this, put it over here, run it. Why didn't that copy? Control C, there we go. Control A, Control V, run it. Keyboard shortcut. Okay. Oh, it's printing out a couple things. Let me stop that one print statement right there real quick. Okay. What do we see here? We see the same choices as we saw before with those 4 NFL teams. And now we're looking for cowboys, lowercase cowboys. And we're saying, just give us the top one. So this is basically like extract limit 1. So this extract 1 is just kind of a short version of that. Just to be very clear on what I'm saying, if I were to say print process extract cowboys choices limit equals 1, this should give me the, oh, what am I doing wrong? Oh, it's a, got it. Gives me the same result, right? It's the same thing. So anyway, again, this extract 1 is simply a shorthand version of extract limit 1. Okay, so that is extract 1. That's useful if you just want to say, okay, I have this string, I have a big list of strings. I just want to find the one that's most like the string I have already. Give me that option. Here it is. Boom. Okay. Now, these extract, the extract 1 and the extract, they use a pretty complicated algorithm to compare strings, the string that you give it and all the choices. Let me show you real quick what that algorithm is like. Here it is. It's W ratio. Return a measure of the sequences similarity between 0 and 100 using different algorithms. Steps in order to occur. First, full process with utils on both strings. Short circuit if this makes either string empty, meaning stop the function if either string ends up being empty after this step. Take the ratio of the two processed strings. Basically, we're doing the simple ratio. Run checks to compare the length of the strings. If one of the strings is more than 1.5 times as long as the other, then use partial ratio comparisons and scale the results to 0.9. If one of the strings is over 8 times as long as the other, instead scale to 0.6. Then run the other ratio functions. If using partial ratio, call partial ratio, partial token sort ratio, and partial token set ratio. Scale all of these to the ratio based on the length. Again, either 0.9 or 0.6, depending on the length of the two strings in comparison to each other. Otherwise, call token sort ratio and token set ratio. All token-based comparisons are scaled to 0.95. And then you take the highest value of all these results and round it and return it as an integer. It's a pretty complex algorithm to figure out that it uses with the extract and the extract 1. But you can specify a different comparison algorithm if you want. So if you, for example, you can say, okay, here is Cowboys, here are my choices, the 4 NFL teams. I want the one that has the highest score, but you need to use the token set ratio. So when I run that, I get back a score of 100. This 90 is coming from the previous print statement there. Let me just comment that out, rerun it. There we go, reran the script, my keyboard shortcut. Yeah, so now we get a score of 100 because we use this this other algorithm that we saw a second ago, the token set ratio. Okay, but if you don't specify a score, then it does that pretty complex one we just walked through a second ago, and it decides that it has a score of 90. That Dallas Cowboys has a score of 90 in comparison to just lowercase cowboys on line 7. Okay. If you'd like to look at that, you can now. Pause the video and look at that. Or again, you can look at my solution file in the CMS. And yeah, there's the default score that I just showed you, that somewhat complex algorithm. Okay, formative quiz, which means just to see how you're doing. There's no points or anything associated with this. With the partner, with yourself, whatever, discuss what the 4 functions would return for the following pairs of strings, and then check your guess by using the 4 functions. Let's just go pair by pair. So here's the first pair. Just think through. Looking at the 4 main functions that we saw, the ratio, partial ratio, token sort ratio, and the token set ratio, what would each one, you don't have to give the exact number, but like just think through, would this be a high score or a low score or somewhere in the middle? Like, you know, approximately what's going to happen here. So pause the video here and look at these 2 strings, this first pair, for a couple minutes. Ready, set, pause. All right, welcome back. Well, they're pretty darn similar, right? The only difference is the punctuation at the end. Linguistics is the study of language, period, versus exclamation point. So the simple ratio will be pretty darn high, right? It's going to be really quite high, although not 100%. Why not 100%? Because these two characters are not identical. I mean, they're just different, right? So they're not going to be, it's not going to be 100%. And the partial ratio also is not going to be 100% because, well, both of these are the same size, the same length. And so the partial ratio is just going to be basically the same ratio, the same score, I believe, is the ratio. Now, the token sort ratio, what's going to happen? What is going to happen if we tokenize them and then sort them? And when we tokenize, we're going to get rid of punctuation altogether. So that means we're going to end up with 100%, or not, it's not percent, 100, a score of 100. Okay, for both the token sort ratio as well as the token set ratio. Let me just show you my solution file that I have that coded up. Let's grab those two strings like that, bring it over into my little main chalkboard area, run it. Okay, so these are the scores that come out. For simple ratio 97, partial ratio 97. For token sort and token set ratio, we have 100. Yep, that is what we have there. I'd like to pause the video and look at that and digest it more. Go ahead. Okay, let's try the next pair. The next pair says computers are awesome, like sweet, whereas the second sentence has a second sweet there. Pause the video and just think through, okay, what's going to happen with the simple ratio versus the partial ratio versus the token sort ratio and the token set ratio. Just to review these, this gets a score of how close they are. Probably the most like pure Levenstein distance, although it gives you a score between 0 and 100. The partial ratio tells you whether how much of the shorter string is embedded within the larger string. And if it's completely embedded, like the entire shorter string is embedded completely without a change of alphanumeric nor spaces nor punctuation within the larger string, it'll return 100. The token sort, to review, first of all, tokenizes, which means breaks up into words, gets rid of punctuation, and then sorts them in alphabetical order, and then finally compares them. And then the token set ratio is very similar to the token sort, but it gets rid of duplicates before it compares them. Okay, so take a minute here, pause the video and look at that pair right there. All right, let's take a look here at my solution file. We can just look right at these two sentences, copy this over here, boom, boom, run it. Okay. I mean, I have the output already listed there as a comment to the right of the code, but here are the two sentences, right? And the simple ratio gives us a score of 92. So very similar, right? There's these extra 6 characters, the space, and 5 alpha characters. On the partial ratio, we get 100%. Why is that? 100% on partial ratio. Well, because the entirety of the shorter string is within the larger string. Right, that's the score of 100. The next one down is the token sort, and we get a score of 91. Because after we tokenize this and get rid of the punctuation and then sort them, we have an extra sweet there. But the token set ratio gives us a score of 100 because it gets rid of that extra sweet, and that's why they turn out to be identical and therefore get a score of 100. Okay, you can pause the video if you like to look at that and digest that a bit more. Okay, let's get looking at this one here. What's going to happen here? Again, you need to be aware that tokenizing means break up on white space. So that is an important clue here on what's going to happen with these two strings. Okay, pause the video and try and think through what each of these 4 functions will do with these two strings. Down here, the A through Z and Z through A with spaces. Ready, set, give it a think. All right, welcome back. Let's take a look at what is going on with these strings here. All right, so for the first two, the ratio and the partial ratio give us a score of 49 out of 100. And I believe the reason is because the spaces are identical. Everything else has to be substituted for something else. The A has to be substituted for a Z, but the next character, which is a space, is identical. And because there's one fewer space than there are characters, letters, we end up at 49 out of 100. The token sort and token set ratio end up at 100 because when we tokenize on the spaces and then sort them in alphabetical order, the second string gets turned into the first string, right? It just flips, it goes from, Z to A and flips it around to A to Z, just like string one is, right? And then the set ratio, the token set ratio is the same thing here. There's no duplicate character in here. So, okay, so that's why we end up with 100 with those two second ones, but 49 with the two first ones there. Okay, if you like this, pause the video and digest that more, go ahead and do so now. All right, one more little question here. What's going to happen to these? Now, these are considered one word because there's no spaces. This is one word. This from A to Z without spaces is considered one word. And Z to A is considered one word as well. So what's going to happen here with those four functions up here? Give it a think. All right, let's take a look here on what happens with those words, or not those quote unquote words. And I have the output already listed there to the right as comments, but all of them are 4 out of 100, very low. And honestly, I'm not even sure why it gets to 4. I'm not totally sure why. But yeah, they all are very low at 4 out of 100. Now there's no tokenizing to happen because there's no space in here. And so it doesn't sort these letters because they're not word. I mean, it doesn't rearrange the letters. It just takes the whole word, and from A to Z is one word and Z to A is another word. And so it doesn't do any more sorting of those than doesn't do any sorting of the letters themselves. So anyway, the take home message here is these are very not similar. Okay. All right. So that is just a little comprehension check for you on those 4 functions, these kind of main 4 functions here. And here's a brainstorming activity. What applications, possible applications of fuzzy string matching can you think of? I have a few ideas here, but why don't you take a think here? Just stop and think through what you could use fuzzy string matching for. Well, welcome back. I have a few ideas. Spell checkers. Right, I believe spell checkers are based on fuzzy string matching. I'm using a big list of words. For example, the one we saw in lesson 5.1 about file input and output was this big massive list of like 200,000 words here. That is at the publisher website of our textbook. Just a big massive list of English words, like 200,000 words, 200,000 lines here, each line with its own word. And so I assume word processors that have spell checking ability have some part somewhere in their code that does fuzzy string matching for each word and says, do you find this word in the big list? If not, mark it with like a red squiggly. And if you right click, it may list some suggested words. Like, I think you're looking for this word. I assume those suggested words are based on fuzzy string matching with a high score. Kind of like the extract, like, the extract function that we saw earlier. It's probably like extract with like a limit of 2. Like, give me the top 2, maybe 3, limit of 3 words that are like this other word. And by the way, I think you can also put in a limit on how, like what score you want the results to have, like a minimum score. You have to have at least a score of 80 to be returned. I assume that is what's happening with spell checkers. I don't know totally for sure, but I assume that's what's happening. Another possible application of fuzzy string matching is when you need to join two tables based on a column, but you're not sure, you can't count on the strings in those two columns being identical. This might be useful for like a customer relationship system, a CRM management system, customer relationship management system, where you have like customers from this part of the company that, there's a CRM over here. Once again, that stands for customer relationship management system that has, certain titles of companies or customers. And this other database within the same company has slightly different entries for the companies. Then fuzzy string matching might be a way to bring those together. So for example, going back to the Cirque du Soleil, if in one database we have Cirque du Soleil's Arcana New York, and in another database we have Cirque du Soleil dash as Arcana, we could use fuzzy string matching to say, oh, these are the same thing. So let's bring those together. And that could be a possible application when you have like two tables or two databases that have basically they're pointing to the same entity, but the strings that identify that entity are not identical, but close. Here's an example. I linked to an example here on Stack Overflow. It's a good example here. So for example, Microsoft, Google, Amazon, IBM, and that's like one database, like one table. And the other one has kind of misspellings or abbreviations or something, or misspellings and abbreviations, or, you could use fuzzy string matching to say, oh yeah, these are the same entity, and put a minimum score of 80. And that's interesting that here the IBM did not have a minimum score of 80 with BIM there. Okay, so that is a quick rundown of fuzzy string matching. So at this point, you should be able to use fuzzy matching, string matching, to determine the similarity of strings based on edit distance. Okay. All right, well, that brings us to a conclusion of lesson 12.2. As always, I'm super happy to help if you want to come into my office hour or that of my TA. All right, see you next time.